Recently in class we did example 2.8 on, or 2.7, excuse me, on page 56, and it was a fairly straightforward example of a common free fall situation from an object, a ball, being thrown up, coming back down, and being allowed to go below the reference point of where I originally threw it. We solved for several things in that example, and now this next one is just really an extension of it, but some basic algebra you might not have to use, since maybe like algebra 2 comes into play here. So in example 2.8, it asks us about the same ball, and we want to find its time, t, when it is a displacement of -5 meters from where I originally threw it. So this line being representing the railing in the problem. So essentially we want to find when it is at -5 meters. We can still use several givens from the last example. The fact that it was thrown up at 15 meters per second, and since this free fall, g is equal to -9.8, forgot the units on there, meters per second squared. And like always, we now go to our four uniform acceleration equations tweaked for free fall, and we should quickly see that this second formula is going to be the only one that's going to be able to work for us. But we've got a little bit of a problem here as far as ease of solving compared to the others. We notice that t is my unknown, and vy initial was not 0. So this t doesn't wipe out like in some problems when we drop did. So what issue that creates is solving for t. We got a t to the first power, t to the second power, and we can't exactly isolate one of those. This we could easily if this side was equal to 0, but delta y is not. So what it leads us to is figuring that we have a full quadratic equation that we must solve using the quadratic formula. So let's review that very quickly. What we will do once we realize we have to use the quadratic formula is plug in the values. And if you remember back this far, to use the quadratic formula we need to get everything in descending order equal to 0. So I'm going to shift everything to the left side, and now our review of the quadratic formula solving for the variable, which in this case is t. And if you recall, the b's, a's, and c's just represent the coefficients on these values with their signs included, so be careful you have all the correct signs taken with it. So once we identify a, b, and c from the descending order that we have here, the a is always a coefficient on the squared term, the b is always the coefficient on the first powered term, and the c is always the coefficient, or actually the constant, which has no variable left next to it. So now we just simply, if you remember that stuff, plug in. So t will equal -b, which b is already a -15, so when we run the math those will cancel out, plus or minus the square root. See, if you remember what this was called, it was called the discriminant, what's under the square root from math class, but it doesn't really matter if you remember that or not. So -15.0 squared minus 4 times the a value, which was 4.9, times the c value, which is a -5.00. Not a ugly looking math, but it's not too bad. All that divided by 2 times 4.9. And if you recall, most commonly we get 2 answers when using the quadratic formula, because the plus or minus, the only time you wouldn't if your discriminant was 0. But you're typically going to get 2 different answers, and we need to decide which one's going to be the right one. When solving it both ways for the plus or minus, we get t is either equal to 3.36 seconds, or t is equal to -0.30 seconds. And at this point, we just got to use a little bit of common sense of which one's going to be my right answer. As we said, for various reasons in the past, t can't be negative. So this answer just is an insignificant outcome, and our true answer of when that ball is going to be -5 meters beneath where I originally threw it is going to be at 3.36 seconds. Yay.